In today's video, we'll be studying thermodynamics, and here we have the outline of all we'll be discussing: an introduction to thermodynamics, thermodynamic systems, the first law of thermodynamics, enthalpy, entropy, second law of thermodynamics, free energy, third law of thermodynamics, and finally, thermodynamic free energy. Now, earlier on in this playlist, we studied chemical kinetics. Okay, and when we studied chemical kinetics, we were basically studying the speed of a chemical reaction. So the time rate of a chemical reaction, how fast a chemical reaction proceeds. So we saw that chemical kinetics has to do with speed. And in that regard, we're considering whether a reaction would be fast or whether the reaction would be slow. Now, in today's video, as I stated earlier, would be studying thermodynamics. Now, unlike chemical kinetics, which is the study of the speed of a reaction, thermodynamics is the study of the spontaneity of a reaction. We have thermo, and then we have dynamics. Now, anytime we hear the word thermo, thermometer, it has to do with heat and temperature in some cases. Now, thermo has to do with heat, and when we hear the word dynamics, this has to do with movement. Okay, so we generally hear things like static and dynamic. Static would be, of course, there would be no motion for a static process, and then dynamic would have to do with movement. So basically, it simply means heat movement. Now, as we would go on to see, the direction of heat flow determines whether a reaction would proceed spontaneously or not. So hence we can say that thermodynamics basically deals with spontaneity. Okay, so we probably know that heat would generally flow from a hot body to a cold body. In other words, when heat flows from a hot body to a cold body, such a reaction is likely to be spontaneous. However, when the heat flow is in the reverse direction, where heat is flowing from a cold body to a hot body, we know that such a reaction is not spontaneous. Now, this brings us to the idea of spontaneity. What exactly does it mean for a reaction to be spontaneous, and what does it mean for a reaction to be non-spontaneous? Now, a spontaneous reaction is a reaction that proceeds without intervention. Okay, so it proceeds without intervention. Now, the intervention in this case would be in the form of energy input. Okay, so this type of reaction would proceed without any form of energy input. It would proceed randomly, spontaneously. However, a non-spontaneous reaction would not proceed without an intervention. In fact, a non-spontaneous reaction would require a continual input of energy in order for it to proceed. Okay, so this is what it means for a reaction to be spontaneous and for a reaction to be non-spontaneous. A very clear depiction of spontaneity and non-spontaneity would be taking a look at this waterfall. Now, here in this waterfall, we can see water flowing from up down. Okay, so we can say water is flowing downhill. Water is flowing from a place of higher potential to a place of lower potential. Okay, so we can see the water flowing in this direction. Now, in order for us to reverse the direction of the flow of water, so we want the water to flow from low to high, we would need, say for example, a pump. Okay, we would need a water pump in order for us to make this water to flow from a low point, so that would be from this point, from this low point to this high point. Would need a form of energy input, in fact a lot of energy input. Now such a reaction would be non-spontaneous because we need an energy input. However, the natural flow of the water is from high to low and there's no energy input required. It just proceeds spontaneously. Hence, it's a spontaneous process. Okay, so that's the whole idea of spontaneity, whether or not a reaction is spontaneous. Now, so far, all that we have been considering, we did see that heat has been a major factor. So we considered heat and potential in the case of the waterfall. Now, heat is not the only factor that affects the spontaneity of a reaction, as we'd go on to see. There are certain other factors that affect the spontaneity of a reaction, such as entropy and so on. So we'll go on to see all of this in this video. We have seen a basic introduction to thermodynamics and what it's all about. Now, before we go on to take a look at our next subtopic, which would be thermodynamic system, it's good for us to take note of this very important fact. And that fact would be that spontaneity is not synonymous to speed. This simply means that simply because a reaction is spontaneous, in other words, that reaction would proceed without any form of energy, it doesn't mean that a spontaneous reaction is necessarily a fast reaction. So this means that thermodynamics does not necessarily correlate with chemical kinetics. Okay, so a reaction could proceed spontaneously. However, it could be a very slow reaction. Take, for example, the radioactive decay of uranium. So we have uranium 238. Now, in the spontaneous decay or the spontaneous radioactive decay of uranium, of course, it's a spontaneous reaction. It proceeds without any form of energy input. However, the half-life of this radioactive decay is about 4 billion years. So we can see that although this reaction is indeed a spontaneous reaction, it's not necessarily a fast reaction because the half-life of the reaction is about 4 billion years. Okay, so spontaneity is not necessarily an indication of the speed of a reaction. It's very important for us to take note of that. Now let's move on to study the types of thermodynamic systems that we have. Now, for this video, we'll be considering three types of thermodynamic systems. This would be the open system, then we have the closed system, and lastly, we have an isolated system. Now, what exactly is a system? As we go on in our study in this video, we'll be making use of three major terms or three basic terms. This would be system, surrounding, and lastly, the universe. A system is that body that is under consideration. Okay, so it's basically the body that is under consideration. Body under consideration. Now, body under consideration simply means that it's the body that we are studying. So a system could be a test tube. Okay, it could be a test tube with certain reactions going on in such a test tube. This would be the system. Now, given that we have this test tube, what exactly would be the surrounding? The surrounding would be everything within the vicinity of the test tube. Okay, so vicinity. Now, the universe would be both the surrounding and the system. Okay. Now, going back to the types of system that we have the open system. Now, literally, it's as the name implies. When a system is open, it's able to exchange matter as well as energy. So, matter and energy is able to be exchanged. Now, taking a look at a closed system, a closed system is only able to exchange energy. Okay, so there's no exchange of matter. It's only able to exchange energy. And as we might expect, an isolated system is neither able to exchange energy nor matter. Okay, so there is no exchange. Now, of course, the exchange that we are referring to would be between the system and surrounding. So let's take, for instance, we have this test tube. Okay, we have a test tube that looks like this. Now, in this test tube, we have reactions going on, and as the reaction proceed, we have gas being given off. Now, gas would be matter. Okay, now in the process of the reaction, heat is lost by the system, so we have heat loss. Now we can see that in this particular system, which is a test tube, we can see that there is an exchange of matter. So the test tube is giving out matter to the surrounding, and there's also an exchange of energy in the form of heat. So the test tube, which is the system, is giving out heat to the surrounding. So we can see that there's an exchange of both matter as well as energy. Now in a closed system, take for instance um we cover the test tube. Okay, so we cover the test tube. So the matter is intact. The gas that is produced stays within that test tube. So the gas stays within the test tube. All the reactants and all the products, they all stay within the test tube. There is no exchange of matter in this system. However, because this glass test tube is not insulated, it's still able to give off some heat to the surrounding, or it may even be able to receive some heat from the surrounding. Now we can see in this case that although there is no exchange of matter, there is indeed an exchange of energy in the form of heat. Okay, so this would be a closed system, and an isolated system would be one where there is no exchange of matter and there is no exchange of heat. So take for instance, we have that this system is insulated. Okay, we have this system insulated against any form of heat gain or heat loss. This, for example, would be an isolated system. All right, so we have taken a look at the introduction to thermodynamics as well as the thermodynamic systems. Now, very quickly, let's take a look at the first law of thermodynamics. Now, one of the first laws would come across in physics and maybe in basic science would be the first law of thermodynamics, and we're probably very familiar with that law. Is one of the laws of conservation. So when we're looking at the laws of conservation, we would basically be considering matter, and then we're also considering energy. And in our study of physics, perhaps a very general definition of physics would be that physics studies matter as it relates to energy. But of course, we're considering this from a biochemical point of view. Okay, now the first law of thermodynamics is one of the laws of conservation. Now, basically, what the law says is that energy can neither be created nor destroyed. It goes on to say that although energy can neither be created nor destroyed, energy can actually be converted from one form to another. Now, this is the first idea of um, the law of thermodynamics that would mostly come across, that energy cannot be created or destroyed, it can only be converted from one form to another. As I said earlier, it's a conservation law. It's a law that energy is conserved in a system. Now, for this video, we'll be going further into this law, more so the mathematical aspect of the law. Now, in that regards, would be saying or would be considering the fact that the first law of thermodynamics has to do with the change in internal energy. So change in internal energy. This is the Greek symbol delta, and it's used to represent change. Okay, so change in internal energy, which would represent mostly as change in U or change in E. Now, the internal energy is basically all possible forms of energy that could be contained within the system. So it could be kinetic energy, it could be potential energy, but all the forms of energy that could be contained in a system would be the internal energy of that system. Okay, now would also be taking a look at heat energy. Okay, so heat energy, which would mostly represent as Q, and lastly would be taking a look at work. Okay, this would mostly be presented as W, phrasing the first law of thermodynamics, so to say, or a more mathematical aspect of that law would be that the change in internal energy of a thermodynamic system. Okay, earlier on we considered the types of thermodynamic system. So a change in internal energy of a thermodynamic system is equal to the amount of heat added to the system or lost by the system, so Q, plus the work done on the system or by the system. So we have heat gain or heat loss, work done on, or work done by. Now, as we would go on to see, different texts have different sign conventions for work. But for heat energy, usually a heat gain would have the positive sign and a heat loss would have negative sign. However, some text would have work done as positive and some text would have work done as negative, while some text would have work done by the system to be negative and some would have this to be positive. But for the most part of this video, the sign convention that we'll be using is that we'll be taking work done by the system to be positive and work done on the system to be negative. However, the signs convention for heat would remain the same as positive and negative. Another way to state the first law of thermodynamics would be to say that the change in internal energy of a system is equal to the heat transfer. Okay, so the net heat transfer into the system minus the net work done by the system. Also, we have that the change in the internal energy is equal to the final internal energy minus the initial internal energy. So it's good for us to take note of this. Now let's take a look at this practice problem. And the question says, suppose there is a heat transfer. Okay, so we have a heat transfer of 40 joules to a system. So this would be heat gain. While the system does a work of 10 joules. So 10 joules, the system does the work. Now later there is a heat transfer of 25 joules out of the system. So this would be heat loss. Well, there is a 4 joule work done on the system. So we have 4 joules done on work done on the system. The question says, what is the net change in the internal energy of the system? What is the net change in the internal energy of the system? So we're looking at change in U. Now, this is where we have the sign conventions come into play. Now, there are two ways we could answer this question. So this is what happens initially. Initially, there's a heat gain and a work done by the system, and later or finally, we have a heat loss of 25 joules and work done on the system being 4 joules. Now, taking a look at our sign conventions that we earlier considered were that firstly, we have heat gain to be positive and heat loss to be negative. Then we have work done by the system to be positive and work done on the system to be negative. Okay, so these were our sign conventions that we considered initially. Now, in that regards, we would have that we could calculate the total or the net heat gained or lost by the system. Okay, so this would be the sum of all the heat gain or loss. Okay, so we considered heat gain to be positive. So we have positive 40 joules, and then we considered heat loss to be negative, would be negative 25 joules. Now we'd have this to be 40 minus 25, which would give us 15 joules. Now, taking a look at the next part of the question, which would be the network. Okay, so we have the network done either on or by the system. The network is going to be 10 joules, positive 10 joules, because it's work done by the system, and negative 4 joules, work done on the system. So this would give us 6 joules. Okay, so we have 15 joules and 6 joules. 15 joules of heat transfer and 6 joules of work done. Coming down to the change in internal energy, which would be equal to Q minus W, we would have this to be equal to 15 joules minus 6 joules, and this would be equal to 9 joules of change in internal energy. Okay, this is one way to solve the question. So, of course, for the net heat, it was basically Q1 plus Q2, and for the network, it was also W1 plus W2. However, because we already have our sign conventions, here it was 40 joules plus 25 plus minus 25 joules, and that's basically why we have simply 40 minus 25 because of our sign conventions. The sign conventions will still hold, although we have a positive sign here. Okay. Initially, we solved the question by calculating the net heat and the network, and then we used our two values to calculate the change in internal energy. Now, another way to solve the question is to work with the initial energy, the initial internal energy of each of the processes, and then sum them up. Okay, so for that, we would have that the change in the internal energy would be the heat minus the work. Okay, so we would basically have this to be 40 joules, positive 40 joules minus positive 10 joules, minus 10 joules, and this would give us 30 joules. Okay, and then for this side, we would have negative 25 joules minus negative 4 joules. So this would give us negative 25 joules plus 4 joules, and this would give us negative 21 joules. Okay, and of course, we would come back to basically finding the net. Okay, so the net change in internal energy. The net change in internal energy would be basically to sum up these two internal energies. So we would have this to be the net change in internal energy would be 30 joules plus minus 21 joules, would simply be minus 21 joules, and of course we would have our answer to be 9 joules. So we would have this to be negative, and then we would have this to be positive. Okay, now we would solve the question again and see if with this change in sign convention we still have the same answer. So far, we have been working with our sign convention to be work done by the system to be positive, and work done on the system to be negative. Now, what happens when we change our sign convention? So let's change the sign convention such that work done by the system be negative and work done on the system be positive. Now, so far we have been working with the change in internal energy to be equal to heat minus work. Okay, now since we have changed our sign convention, It means that the change in internal energy would now be defined as the heat plus work. In that regards, a way to solve the question would be first to get the net heat. Okay, so first get the net heat, which would be 40 plus minus 25 joules, which would give us 15 joules. Okay, then get the net work, which would be negative 10 joules plus 4 joules. Okay, this would give us negative 6 joules. Now, of course, as I stated earlier, since we have changed our sign convention, we'll now be working with this. Working with that would have that the change in the internal energy would be equal to 15 joules plus negative 6 joules. And of course, this would give us 15 minus 6, which would be equal to 9 joules. So basically, we have 9 joules of change in internal energy. Okay, and solving it in the different way where we simply work with each of the processes. Another way to solve the question would be to consider each of the processes. So to consider Q1 and W1 and Q2 and W2. Okay, so in this regard, we'll solve the question. The change in internal energy for the first process is going to be Q1 plus W1. And then, of course, we would find that for the second process, which would be Q2 plus W2. Now, the change in internal energy for the first process is going to be 40 joules plus negative 10 joules. Okay, our sign conventions will still hold. This would give us 30 joules. Okay, so we have 30 joules here. And in this case, we would have negative 25 joules, plus positive 4 joules. This would give us negative 21 joules. And of course, since we already have the change in internal energy for each process, we'd simply add these two values together. So we would have 30 joules plus negative 21 joules, and this would give us 9 joules, which we got earlier on. Okay, so it's very important for us to take note of these two examples. So basically, when we're working with work done by the system to be negative, then we'll be working with Q plus W. However, when we have work done by the system to be positive, then we'll be working with Q minus W. So these are basically the sign conventions. Of course, if work done by the system is negative, then work done on the system would be positive and vice versa. Okay? Alright, so far we have considered the first law of thermodynamics. Now let's take a look at enthalpy. Now, enthalpy is a measure of the energy in a thermodynamic system. It's basically equal to the total heat content of a system. Mathematically, it's represented as H, and it's equal to the sum of the internal energy and the product of pressure and volume. Alright, so from our knowledge of general physics, we know that work is equal to the product of force and displacement. Now, force is related to pressure in this way. So basically, pressure is equal to the force divided by the area, which implies that force would be the product of pressure and area. Now, we can replace this into what we have here, so that we would have that work is equal to product of pressure and area as well as displacement. Displacement is a form of distance. It's distance in a particular direction, so it's a vector quantity. So we could simply represent displacement with its magnitude, which would be d, okay, simply distance. So work would be the pressure area multiplied by distance. Now we know volume to be equal to area, or the area of the cross section multiplied by the height. Okay, this is kind of like a general formula for volume. So it means that we could replace area and distance with volume. So basically, work is equal to pressure times volume. It's very important for us to take note of the fact that when we have a positive change in volume, we would have a negative work. Okay, and when we have a negative change in volume, we would have a positive work. Okay, so it's very important for us to take note of this, that the sign of change in volume and work is always opposite. Okay, now coming back to our enthalpy, which we define as H to be equal to the internal energy, the sum of the internal energy and the product of pressure and volume. Coming back to this, we already defined the internal energy earlier on as the heat loss or heat gain minus the work done by or work done on the system. Okay, so we'd have that the enthalpy is equal to Q minus W plus PV. Now, it's important for us to take note of two types of work. So basically, we have useful work, which would represent as W1, and then we have the pressure volume work, which we already represented as PV. Okay, now the work that we have here from internal energy is the sum of both the useful work and the pressure volume work. Now, the useful work would be the other forms of work, all other forms of work other than the pressure volume work. That would be the useful work. Work done on the system that doesn't necessarily lead to an increase in volume, and work done by the system that doesn't necessarily have to do with pressure and volume. That would be the useful work. Okay, and what we have here, W, is the sum of both the useful work as well as the pressure volume work. It's important for us to take note of this. And now, at constant pressure, we have that this total work would be the sum of the useful work as well as the pressure times the change in the volume. It's important for us to take note of this. Now, bringing this back to what we have here, it means that at constant pressure, we would have that the enthalpy, which is H, would be equal to Q, the heat, minus what we have here, so W1 plus P change in V, and then plus P change in V as well, because pressure is constant. So we would have that the enthalpy would be equal to Q minus W1, okay, then minus P delta V plus P delta V. Notice that this would cancel out. Okay, so this would be equal to 0. And then we would have simply that the enthalpy is equal to the heat at a constant pressure minus all other useful work other than the pressure volume work. So this would be the equation for enthalpy at constant pressure. Now let's take a look at how enthalpy relates to heat. Okay, how it relates to heat. Now this brings us to the idea of endothermic and exothermic reactions. Now in an endothermic reaction, we have a heat gain to the system, and in an exothermic reaction, we have heat lost by the system. In other words, An endothermic reaction absorbs heat while an exothermic reaction gives off heat. Okay? Now, how does this relate to enthalpy? Now, having established that an endothermic reaction absorbs heat, so there's a heat gain, and we already define heat gain as positive Q. Okay? Now, positive Q, or when Q is greater than 0, this has an implication on the enthalpy, and it means that the enthalpy would also be greater than 0. So when we have a positive enthalpy change, such a reaction is endothermic. However, for an exothermic reaction, we have heat loss. So this would be negative Q. In other words, Q is less than 0. This implies that the change in enthalpy would also be less than 0. So when we have the change in enthalpy to be negative, then we have an exothermic reaction. Okay, so far we have considered the introduction, the thermodynamic system, as well as the first law of thermodynamics, and we just considered enthalpy. Now let's take a look at entropy. Now, so far we have been considering the spontaneity of a reaction with regards to heat. So we discovered that basically when there is a heat flow from hot to cold, such a reaction would generally proceed spontaneously. Now, entropy is another factor that determines the spontaneity of a reaction. And entropy is simply the degree of randomness of a system. Now, how exactly does entropy affect the spontaneity of a reaction? As we would go on to see, a system would generally move from low entropy to high entropy. Okay, so a system would generally move from a lower randomness to a higher randomness. Okay, so whenever there's an increase in entropy, which is represented as delta S, when delta S is positive, such a reaction would generally be spontaneous. And when delta S is negative, such a reaction would generally be non-spontaneous. This is because of the degree of randomness of a system. So it means that a system is likely to move from liquid to gas because the particles in a liquid are less random than the particles in gas. Also, it means that a system is likely to move from solid to liquid because the particles within the solid are less random. They are more arranged than the particles within a liquid. And this is why if we have an ice cube, it's more likely that the ice cube would melt into liquid water than for the reverse process to take place. Okay, so this from ice to water is more so a spontaneous reaction than from water to ice. Also, it's very important for us to take note of particularly considering from liquid to gas. Now, taking a look at condensation, we have a movement from gas to liquid. Okay, now as I stated earlier, a system would generally move from lower randomness to higher randomness. However, the conversion from gas to liquid doesn't obey that law. Now, as we would go on to see, not only does the entropy of a system affect the spontaneity, the entropy of the surrounding also plays a role in the spontaneity of a reaction. Okay, so in this case, although we have a negative entropy, although we have a negative change in entropy for the system, which would be moving from gas to liquid, from higher to lower, we actually have a positive change in entropy for the surrounding. Okay, and that is partly because this reaction is an exothermic reaction, so heat is given off in the process. Okay, so the overall entropy, the overall change in entropy, which would be the change in entropy of the universe, is actually positive. hence the reaction is still a spontaneous reaction. Okay, we'll get to look at all of this in details. Take for instance, you have a hall or you have a large room. So this would be a large room, and you have chairs arranged in this room. Now you have a group of people, so you have this group of people, and you ask them to come into this room. Now, when this group of people come into the room, it's very unlikely that they would form straight lines. Okay, so that it's very unlikely that they would file up in straight lines. However, it's very likely that these people would simply stand randomly throughout this large room. So people might meet other people that they know. They would stand randomly in groups, forming smaller groups, discussing. It's very likely that there would be a random arrangement of people throughout this large room. Okay, so that would be spontaneous. Disorderliness is more spontaneous than orderliness, and that's why the system is likely to move from a place of lower um from a place of lower randomness to a place of higher randomness. Okay, so it's less likely that they would line up in straight file, and this is basically how entropy plays out. Okay, let's take a look at the second law of thermodynamics. The second law of thermodynamics simply has to do with how spontaneity relates to entropy. Basically, according to this law, a process is spontaneous if the entropy of the universe increases. And this further buttresses our idea of condensation and why condensation takes place spontaneously, even though we have a decrease in the entropy of the system. Okay, so basically, what determines the spontaneity of a particular reaction or a particular process is the overall entropy. Okay, so the entropy of the universe and not necessarily the entropy of that system. So, generally, when there's an increase in entropy of the universe, such a process or such a reaction is spontaneous. Now, we have the change in entropy of the universe to be equal to the change in entropy of the surrounding plus the change in entropy of the system. Now, so far, we have considered entropy as it relates to randomness. And this randomness is in terms of motion. Alright, so it's important for us to take note of the fact that the change in entropy of the system is equal to the quantity of heat divided by temperature. So this is of the system. The change in entropy of the system depends on temperature. Now, the sign for the change in entropy of the surrounding depends on the direction of heat flow. In an exothermic reaction, where we have negative Q because we have heat loss, we have the change in entropy of the surrounding to be equal to negative Q divided by T. And this, of course, is measured in Kelvin. And for an endothermic reaction, where we have heat gain, positive Q, the change in entropy of the surrounding would be equal to positive Q divided by T. Okay, so it's important for us to take note of this relationship. Okay, so we have the change in entropy of the universe, then we have the change in entropy of the system, and then we have the change in entropy of the surrounding. When the change in entropy of the system is positive and the change in entropy of the surrounding is positive, it implies that the change in entropy of the universe is going to be positive, and such a reaction is going to be spontaneous. Remember that the change in entropy of the universe is equal to that of the surrounding plus the system. Now, how about when we have the change in entropy of the system to be negative, and we also have the change in entropy of the surrounding to be negative? Now, negative plus negative would give negative. So basically, we would have negative plus negative. This would give us a bigger negative. So the change in entropy of the universe would be negative. And since the change in entropy of the universe is negative, and we have already established that a process is spontaneous, if the change in entropy of the universe is positive, it means that such a reaction would be non-spontaneous. Okay, now in a case where we have the change in entropy of the system to be positive and the change in entropy of the surrounding to be negative, now would this reaction be spontaneous or non-spontaneous? Well, it depends, because we have established that that of the universe is equal to surrounding, or system and surrounding. Okay, it means that if we want a positive value here, given that this is positive and this is negative, it means that the entropy, the change in entropy of the system must be much larger than the negative value that we have here in terms of magnitude. So if this is 50, positive 50, and this is negative, then this should be a negative value that is lower than 50. So perhaps negative 45. Okay, now when the value of the change in entropy for the system is much larger than that for the surrounding, even when the surrounding has a negative entropy, the reaction is still likely to be spontaneous. Okay, but of course it depends on that condition that we stated earlier. So this is questionable based on that condition. In a case where we have this to be negative and we have this to be positive, the condition still applies. If that of the surrounding is much larger than that of the system, then of course it would be a positive, it would be a spontaneous reaction, but it's still questionable. So this is basically the interplay of the sign conventions that determines whether a reaction would be spontaneous or non-spontaneous. So far we have considered the second law of thermodynamics. Very quickly, let's take a look at free energy. Now, earlier on in our study, we took a look at two forms of work. We said we have useful work and we have the pressure volume work. Now, the pressure volume work is work done to bring about a change in volume, while the useful work is every other form of work other than the pressure volume work. Now, just as we have the useful work and the pressure volume work, we also have a useful energy. And this energy is useful because it is usable. This brings us to the idea of free energy. Free energy is the total usable energy of a system. In other words, is the amount of energy available to do work other than the pressure volume work. Okay, so whenever we have this energy, the free energy, it would be the energy available to do useful work, and that useful work would be work done other than the pressure volume work. This is the whole idea of free energy. Free energy is represented as G, and it's equal to the enthalpy minus the temperature minus the product of temperature and entropy. And this is temperature in Kelvin, and of course we have here entropy. Now, earlier we stated that in order to have a reaction, a spontaneous reaction, essentially the change in entropy must be positive. Now, fitting that into this idea of free energy, so this would be for a spontaneous reaction. In order to have a spontaneous reaction with regards to free energy, we would have that free energy is equal to entropy, or rather enthalpy, minus the temperature. But of course, for a spontaneous reaction, entropy must be positive. So we already have this established as positive. The criteria for a reaction to be spontaneous with regards to free energy is that the change in free energy must be negative. So we can see the difference in sign convention. So for a spontaneous reaction, entropy is positive and free energy is negative. So it's important for us to take note of that. Let's take a look at the sign interplay for the free energy. We have here entropy, and then we have here enthalpy, so the change in enthalpy. And of course, we have already established that the free energy is enthalpy minus product of temperature and entropy. Okay, so we have this. Now, in a case where we have this value to be positive, we have this value to be negative, what happens? This simply means that we have here negative h, negative ts. This would give us an overall negative g. So g would be negative. And we already established that this would be a spontaneous reaction. Okay, so this would be spontaneous. Now, what happens in a case where we have entropy to be negative and enthalpy to be negative? Okay, so we would have negative h, negative t into negative s, and this would give us negative h plus ts. However, we want to know whether or not our reaction would be spontaneous. So we want to know whether or not this value would be greater than 0. However, for spontaneity, this value should actually be less than 0, so it should be negative. Now, what's the condition for a situation like this to give a spontaneous reaction? For a situation like this to give a spontaneous reaction, it means that this must be less than 0. Now, let's simplify this further. So we have a bit of math coming to play here. Negative h plus ts less than 0. So we would have that ts is less than h. Okay, this is trying to simplify it further when we bring h to the other side. Then we would have that t is less than h over s. It means that when we have entropy to be negative and enthalpy to be negative, the condition for the reaction to be spontaneous is that the temperature in Kelvin must be less than that the ratio of enthalpy to entropy. So let's apply this very quickly. So we have G to be equal to H minus Ts, and then we establish that if H is negative and S is also negative, so enthalpy and entropy, then the condition for this reaction to be spontaneous is that the temperature must be less than the ratio of H to S. Okay, so take for instance, we have this to be negative 60 and we have this to be negative 30. It means that the ratio of these two would be 60 divided by 30, which is equal to 2. In order for this reaction to be spontaneous, the temperature must be less than 2. Okay, so let's have our temperature to be 1. So T equals 1. Applying that here, would have that G is equal to negative 60 minus 1 times negative 30. So this would be that G is equal to negative 60. So this would be minus times minus, which is plus, plus 30. And this would give us negative 30. Okay, so we can see that we have a negative value of free energy, and hence the reaction would be spontaneous because this condition is fulfilled. Okay, temperature should be less than the ratio of enthalpy to entropy. Now let's take a look at another sign convention. So when we have the entropy and then enthalpy, in a case where we have the entropy to be positive and the enthalpy also positive, of course the free energy is H minus Ts. Okay, so we would have H, positive H, minus Ts. This is the free energy, H minus Ts. Okay, now in order for this to be less than 0, what is the condition? So we would have that negative Ts is less than negative H. We would be dividing through by negative S. And from our knowledge of general mathematics, whenever we divide an inequality by a negative number or by a negative value, the inequality would change to its opposite. So here we have this to be less than. When we divide by negative s, it would become greater than. So T would be greater than H divided by S. Okay, so this is the condition for such a reaction to be spontaneous. When we have both entropy and enthalpy to be positive, in order for the reaction to be spontaneous, that is, in order for the free energy to be negative, then the temperature must be greater than the ratio of enthalpy to entropy. Take, for instance, we have positive 30 to be our entropy, and we have positive 60 to be our enthalpy. So this is H, and then this is S. We said the condition for this reaction to be spontaneous would be that the temperature should be greater than the ratio of these two values. So the ratio of this would be 60 divided by 30, and this of course is 2. So the temperature should be greater than 2. So let's say 3 Kelvin. Okay, so 3 Kelvin is greater. So G would be equal to H minus Ts. This implies that G would be equal to 60 minus 3 times 30, and then G should be equal to 60 minus 90, which is equal to negative 30. Okay, so this reaction would be spontaneous because we have a negative free energy value. In a condition where we have the entropy to be negative and we have the enthalpy to be positive. Okay, so we have G is equal to H minus Ts. Under this condition, we would have that G is equal to positive H minus T times negative S. So we would have that G is equal to positive H plus Ts. Notice that there is no condition under which this could possibly be negative, because we have positive and positive. There is no condition under which this would give us a value less than 0. In other words, this reaction where we have entropy to be negative and enthalpy to be positive is a non-spontaneous reaction. Okay, so it's good for us to take note of that. Now, this brings us to the idea of Gibbs free energy. So far, we have been considering free energy. Now, while free energy has to do with the universe, okay, free energy has to do with the amount of usable energy of the universe. Okay, it doesn't take note of whether we're considering the system or the surrounding or the universe. It's more so the free energy of the universe. Gibbs free energy, on the other hand, is specifically the free energy of the system. Okay, so the change in free energy of the system is Gibbs free energy. So it's important for us to take note of that. In a lot of text, free energy and Gibbs free energy are used interchangeably. Okay, but it's important for us to take note of the fact that Gibbs free energy is specifically the free energy of the system. So all that we have learned so far applies. Okay, so far we have considered the introduction, the thermodynamic system, the first law of thermodynamics, enthalpy, entropy, and then the second law of thermodynamics, as well as free energy. Now, very quickly, let's consider the third law of thermodynamics. Now, for this video, we would not be considering the third law of thermodynamics in details. We would only be taking a look at it on a very basic level. Okay, now what this law simply states is that the entropy of a perfect crystal at absolute zero, the entropy of a perfect crystal at absolute zero temperature is 0. And the entropy of a substance increases with temperature. So entropy increases with temperature. This is the general idea of the third law of thermodynamics. The entropy of a perfect crystal at absolute zero temperature is 0, and entropy increases with temperature. Now, moving on to our next subheading, which would be thermodynamic free energy. Under this subheading, would be considering the relationship between free energy and the equilibrium constant. So far, we have considered the Gibbs free energy or the free energy, and we said for a spontaneous reaction, we have the change in free energy to be negative. Okay, so this would be a spontaneous reaction. When the change in free energy is positive, we have a non-spontaneous reaction. And when the change in free energy is equal to zero, we have a reaction at equilibrium. Now, this brings us to the idea of the relationship between the free energy as well as the equilibrium constant. Now, it's important for us to take note of this formula, which is that the change in free energy, delta G, is equal to delta G naught, which is the standard free energy change, plus RT ln K. Okay, so basically R is a gas constant, and of course we have a temperature at Kelvin, measured in Kelvin. Ln would be the natural logarithm of K, which is the equilibrium constant. Since we're considering a reaction at equilibrium and we already established that the free energy would be equal to zero, it means that this expression is equal to zero. So delta G naught plus RT ln K is equal to zero. This simply means that the standard free energy change, delta G naught, is equal to negative RT ln K. Having established the relationship delta G naught is equal to negative RT ln K, okay, so this is how G naught relates to K. How does K relate to G naught? So we'll be doing a change of subject formula here. Okay, so we divide through by negative RT, so we'd have that ln K is equal to delta G naught divided by negative RT. Now, ln K is the natural logarithm of K, and it's simply log to the base E. E is Euler's number. Now, E is equal to 2.7182, and it goes on in that order. Okay, so ln is logarithm to the base E. Now, logarithm to the base E of K is equal to delta G naught divided by negative RT. Now, from our laws of logarithm, we know that basically how logarithm relates to exponentials. If we have log to the base A of B equals n, it means that A raised to the power of n is equal to B. Now, applying that concept here, this simply means that K, which is the equilibrium constant, is equal to E raised to the power of negative delta G naught divided by RT. Now, let's take a look at how the equilibrium constant relates to Gibbs free energy in terms of different sign conventions. So basically, we have already established that K, which is the equilibrium constant, is equal to E raised to the power of negative delta G naught divided by RT. In an equilibrium reaction where we have A plus B going on to give C, the equilibrium constant would be expressed as K is equal to the concentration of C divided by the concentration of A and the concentration of B. If we had more values of, say, A, B, C, then the equilibrium constant would be the concentration of C raised to the power of C, the concentration of A raised to the power of A, and the concentration of B raised to the power of B. Now, what this simply means is that if we have a K value greater than 1, it means we have more products than we have reactants. It means that the reaction favors the forward direction. Okay, so the forward reaction is favored when we have K to be greater than 1. For example, if we had 8 divided by 4, this is 2 and this is greater than 1. It means we have more products than we have reactants. However, if we have K to be less than 1, say for instance we have 4 divided by 8. This is 1 over 2, and it means that we have more reactants than we have product. The reverse reaction is favored. Okay, and in a case where we have k to be equal to 1, so take for instance we have 4 divided by 4, it means that the reaction neither favors the formation of product nor the formation of reactants. Okay, now having established this relationship, let's take a look at how it plays out with regards to the free energy, the standard free energy change. When the standard free energy change, delta G naught, is negative, we would have that K is equal to E negative into negative G naught divided by RT. In other words, we would have the exponent to be positive because negative multiplied by negative would be positive. We'd have the exponent to be positive, and by implication, we would have k to be greater than 1 because e raised to the positive value would give us a value greater than 1. So when this is negative, k is greater than 1. Now, in a case where we have negative delta G naught to be positive, in other words, when it is greater than 0, we would have this to be k equals E negative positive G naught divided by RT. The exponent would be negative, and being a negative exponent, it means that our value for k would be less than 1. Our value for k would be less than 1, and this means that of course such a reaction favors the formation of reactants rather than the formation of products. And in a case where we have delta G naught to be equal to 0, where we have k equals E delta G naught being 0 divided by RT. Now 0 divided by RT would be 0, and e raised to the power of 0 would be 1. So it means that k would be equal to 1. Such a reaction neither favors forward nor backward reaction. So k is equal to 1. So to summarize this, delta G naught, when it's less than 0, k is greater than 1. When we have delta G naught to be greater than 0, we have k to be less than 1. And when we have delta G naught to be equal to 0, we have k to be equal to 1. Okay, so it's important for us to take note of that. Now, before we round up the video, it's important for us to take note of the fact that when the change in free energy is negative, then we have the reaction is said to be hexagonic. When the change in free energy is positive, the reaction is said to be endergonic. So it's important for us to take note of these two terms. Now, going by our outline, we have come to the end of this video. So far in this video, we considered the idea of thermodynamics. We looked at a brief introduction into thermodynamics where we said thermo has to do with heat and dynamic has to do with flow or movement. So thermodynamics simply deals with the spontaneity of particular reaction. We also went on to see that spontaneity does not exactly correlate with how fast a reaction would proceed. So a reaction could be spontaneous and yet proceed very slowly. Went on to see the three types of thermodynamic systems where we considered the open system, the closed system, as well as the isolated system. We went on to see the first law of thermodynamics where we said energy cannot be created nor destroyed, it can only be converted from one form to another. Then we went on to look at the idea of enthalpy where we said it has to do with the heat content of a particular system. We went on to take a look at entropy and we said it has to do with the degree of randomness of a system, and generally a reaction would proceed from low entropy to high entropy or from orderliness to disorderliness. We went on to see the second law of thermodynamics, and we said, put simply, it has to do with the fact that for a reaction or for a process to be spontaneous, then the change in entropy of the universe must be positive. We went on to see the idea of free energy, and we said is the energy available to do useful work, and we said that useful work is every other work that can be done other than the pressure volume work. We went on to see the third law of thermodynamics. We said we won't be considering this law in details, and simply put, it has to do with the fact that the entropy of a perfect crystal at absolute zero temperature is zero. And then we went on to see the thermodynamic free energy, where we considered how the equilibrium constants relates to the standard free energy change. We have come to the end of this video. If you liked this video, please give it a thumbs up and don't forget to subscribe. Thank you for watching till the end. Bye.